everybody, it's September 10th, 2020. We're continuing the weather unit. Let's start off with a few announcements.
Hey, honey bunnies. Are you ready for a hop and cool announcement? Follow me, this might take a minute.
Alright, first of all, don't forget to complete that daily attendance link. That is mandatory every day and every quarter, so make sure you're getting that done. Also, I'm still upgrading day grades from the redos and the retakes, etc. It's a lot of them, so just be patient. I'll get them in. I'm working. Today's learning targets. We are recognizing still that the sun provides the energy that drives convection within the atmosphere and oceans, producing winds. And we are identifying how global patterns of atmospheric movement influence local weather using weather maps that show high and low pressure and fronts. So that's a new one. We've been doing recognizing that the sun provides the energy for a couple of days, and now we're adding to that knowledge. Your tasks today include this lesson video, your notes on page 13 and 14, and quiz 2 that will be on Schoology. You do need to wait and do your notes before you do that. That will be available and open all the way until next Monday, the 14th. So you have until 11:59 p.m. on Monday to get that quiz number 2 done. But please do your notes first. Your notes should look like this. Again, you can write the question and then you don't have to write a complete sentence for your answer, or you can write all complete sentences and you don't have to write the question. That is up to you. You get to choose how you want to set that up. Do not just write incomplete sentences down that aren't helpful. Plus, you won't get a good grade on your notebook if you do choose to do that, okay? So we saw that air pressure experiment at the beginning of the video, but I want to ask you, do you think the size of the can matters when you do that experiment?
We filled this barrel with a couple inches of water, and we heated it up so it's like turning into steam. And then we're gonna quickly put this can filled with steam into the bucket of ice water, and it should crush. That's because it's going to go through a rapid phase change where the steam is going to condense quickly into water vapor, and pressure inside of the can is going to be less than the pressure from the outside, and it should crush. It should explode. Thank you!
Tight. Twist. Twist.
It's hot. You want to hear it? I don't want to hear it.
That's fine. Squeeze.
Should I sign something? Like,
Insurance.
I want a single. Come on, go!
Patience, patience, my child, patience. Patience.
Try sloshing some more ice on the side.
Oh no, my God, the stopper is getting pulled in.
Yeah, I'm looking a little bit.
Does that mean it didn't work?
No. Throw some water on it. Yeah. Oh no, just grab the ice, and with your hands. That is so wimpy.
Well, I'm scared that it's gonna blow up.
Wait, yo.
Do it. Yeah. Oh. Oh yeah. Oh, I hear it.
So what happened? So we're going to look at what exactly happens when we do the can crusher experiment.
So we have an open can here, and the air, the atmosphere that's being pulled down by the gravity of the Earth is pushing on the outside of the can. But since this is an open can, the air inside, that same air being pulled down by the Earth's gravity, is pushing out. And then we have this kind of equilibrium here where nothing happens to the can. Let's think about those molecules inside of the can and what they're doing. So we have molecules of air, the red are oxygen, blue nitrogen, there's some argon, carbon dioxide, and water vapor. And as they move around, when they're hitting the side of the can, they're creating pressure. That's the air pressure. And that's pushing on the can from the inside. Of course, on the outside, we have the exact same pressure, and that's pushing on the can. Every time those molecules collide with the can, they create pressure as well. So let's think about liquid water. We put a little bit of water in the can, and it sits at the bottom of the can, and then we have the air above it with those gas molecules moving around. But if we start heating those water molecules, so here we have, as a liquid, these molecules are moving around, but they're pretty much staying together. They're not getting too far apart. If we raise the temperature up, it will change from a liquid into a gas, and the water molecules will spread out. When they do that, they'll push all of those air molecules out, and all we'll have inside of the can is water vapor. Let's see that happen. As the temperature increases, you can see the water molecules are spreading out, and they'll force the air out of the can, leaving just water vapor in the can. So now we flip the can over, put it in water. That seals the top so no air can get in, and we've cooled the can. And all that gas, that water vapor in there, changes back to a liquid very quickly. That's important because as a gas, the water molecules were hitting the side of the container and creating pressure. We still have air on the outside, molecules hitting the side of the container, creating pressure, but on the inside, we don't have the gas anymore. We have a vacuum because we've sealed the top when we turned the can over. And because of that, air pressure on the outside crushes the can.
So just what is atmospheric pressure? Atmospheric pressure is caused by weight of air above an area. Pressure decreases with increasing height above Earth. So the higher the elevation, the lower the air pressure. 1 square inch column of air weighs 14.7 pounds at sea level. Air pressure is measured using a barometer in units called millibars. Average barometric pressure at sea level is 1,013.25 millibars, or 29.92 inches of mercury. High pressure is cold, dense air that creates more pressure on the barometer, and low pressure is warm air that is less dense that creates less pressure on the barometer. Pressure systems. A high pressure, as air cools, it becomes more dense and sinks toward the Earth's surface, spinning clockwise. As it warms, it becomes less dense and rises above Earth's surface, spinning counterclockwise, creating a low pressure system. During a high pressure system, the weather is typically good. It's high pressure, happy weather is one way we remember it. It's going to be created by the cooler, denser, heavier air. The air is drier. We get clear, sunny skies and light winds. However, in a low pressure system, we used to get what we call lousy weather. It's created by the warmer, lower density, lighter air. The air is going to be more moist. We're going to get cloudy skies, precipitation, storms, heavy winds. So low pressure, lousy weather, high pressure, happy weather.
Snow day! Ugh! RJ, watch it! Sorry, I'm a little excited for our random day off.
I can't believe there was a snowstorm. It just came out of nowhere.
The snow didn't just come from nowhere. A cold front moved in.
A what?
A cold front. A front is the boundary where two air masses clash, and weather, like snow, occurs. There are warm and cold fronts. I'll demonstrate.
No, don't! Just tell me.
I'm not going to throw it at you. Listen, You know what an air mass is, right?
A big massive blob of air?
Kinda. An air mass is a large body of air that has the same temperature and moisture level throughout. There are 4 different types of air masses in the United States, and each one carries its own temperature and amount of moisture.
So what are their names?
Well, 2 are cold and 2 are warm. The 2 cold air masses are the maritime polar air mass and the continental polar air mass.
What about the 2 warm air masses?
The 2 warm air masses are called the maritime tropical air mass and the continental tropical air mass.
So which ones can I thank for the snow day?
It snowed because one of the cold air masses clashed with a warm one and made a cold front. When that snowball hit you, it exploded, right?
Yeah, and it hurt.
Well, Sam, I think it's instant replay time. Let's say the snowball was a cold air mass and you were a warm air mass. When you both clashed together, a front was made and the ball burst. It snowed.
Oh, that's kind of cool.
Yeah, this snowstorm is a result of a cold front. Cold fronts happen when a cold air mass pushes a warm air mass up. Big puffy clouds called cumulus clouds are formed. When you see dark clouds like those, you can bet you're in for some heavy rain, thunderstorms, or a snowstorm like this.
What happens at a warm front?
A warm front happens when a warm air mass catches up with a cold air mass and slowly climbs up and over it. As the warm air mass passes over the cold air, long, thin stratus clouds stretch out across the sky. A warm front can cause rain and snow too, but it's light and steady, not heavy and stormy like a cold front's weather.
So a cold front means pretty crazy weather that gets me a snow day. And a warm front just means it might still rain or snow, but it won't be as intense. An air mass is a large body of air that has the same temperature and moisture throughout, and there are 4 types of air masses in the U.S. Each one has unique characteristics that hint at where it formed. When 2 of these air masses meet, they form a boundary called a front. It can be a warm front or a cold front, but either way, some kind of weather always happens on a front.
Hey! Okay, I deserved it. It's freezing though. I think I'm gonna head in for some hot chocolate.
Air masses are large bodies of air with relatively uniform temperature and density throughout. They originate over land, and we call them continental when they do, or they originate over water, when we call them maritime. Cold air masses tend to approach from the poles, and warm air masses tend to approach from the equator. Cooler air masses molecules are more dense and flow toward areas that are less dense, warm and rising. High pressure areas move into low pressure areas. During a front, we're going to have 2 air masses that meet. So that's the boundary between the 2 air masses. It's classified by which type of air mass, whether it be cold or warm, is replacing the other. So when you see it on a map, the map symbols point in the direction that the front is moving. And we'll look at that a little closer later in the week. So a cold front, a cold air mass is overtaking a warm air mass. The air behind the front is colder and drier, and the pressure increases. Remember, cooler air is going to be heavier, high pressure. The moist air is pushed up over the cooler, drier air, and clouds and precipitation form. During the warm front, a warm air mass is replacing a cooler air mass. The air behind the front is moist and lighter, and the pressure goes down. It's slow moving, gradual rise of warm air over the cooler air. And the widespread continuous precipitation occurs along and ahead of the front. In a stationary front, we have 2 different air masses, and neither one is really strong enough to replace the other. So they kind of sit there, and we'll get a lot of rain over several days. So it's just a lot of cloudy, rainy days, but nothing really heavy. And then we have the occluded front, where 2 cold air masses converge on a warm air mass. It occurs when a fast-moving cold front overtakes a warm front, pushing it up and over the cooler air. Again, we're going to get storms and precipitation along the front. And after the front passes, usually the sky is clear and dry.